Okay, thank you very much for the introduction. The title of this talk is a method to construct exponential families by representation theory. This is a joint work with Taro Yoshino. First, I introduce myself shortly. I'm a postdoctoral researcher in mathematical science team. My name is Koichi Tojo. My research field is Lie group theory and representation theory, which is a study of symmetry of spaces. These are my hobbies. Recently, I have enjoyed shogi, which is a traditional Japanese board game like chess. This is more complicated and dynamic than usual chess because we can reuse the piece we captured from the opponent. If you are interested in, please play shogi. Then let's enter the research talk. First, we explain our aim of this research and demonstrate a family of distributions on the upper half plane with Poincare metric so that we can share our aim of this research. One of our aim is to suggest good families of probability distributions on important spaces. Not only Euclidean space, but also curved spaces such as sphere and upper half plane. To attain our goal, we propose a method to using representation theory. Here we demonstrate a family of distributions on the upper half plane with Poincare metric obtained by our method. The right side is the upper half plane with Poincare metric. This is a family of distributions on the upper half plane with three-dimensional parameter space. We want to suggest a good families not only upper half plane. Okay. This is a plan of this talk. First, we will talk about background of our motivation. And next, we will explain the method. We call it G-Motage method here. And if we have a time, I introduce related work. In the field of math, first I talk about motivation. In the field of machine learning, learning using a family of probability measures is one of important methods. Here, learning is mathematically to optimize the parameters in the family of probability measures. We often use exponential families as a probability model. This is a good class of families of probability measures. In fact, exponential family are important subject in the field of information geometry and are useful for Bayesian inference and include many widely used families. Family of normal distributions is a typical example of exponential family, and exponential families include Bernoulli distributions and gamma distributions, Wishart distributions, von Mises distributions, and so on. Categorical distribution is a generalization of Bernoulli distributions. Wishart distributions can be regarded as a generalization of gamma distributions. Homogeneous distribution is well studied in the field of directional statistics. Here is our definition of exponential family. We modified well-known definition in the field of statistics for convenience to representation theory here. Roughly speaking, exponential family is a family of distributions having this form, with this exponential form. More precisely, here let X be a manifold and Rx the set of all random measures on X. A subset P consisting of probability measures of Rx is an exponential family on X if there exists a triple mu Vt satisfying the following four conditions. The first condition is mu is a random measure on X, and the second condition is that V is a finite dimensional vector space over R, and the third condition is T is a continuous map from X to V, and the fourth condition is the most important condition, namely, for any element of P in P, there exists an element of dual space and dual of vector space V such that this equality holds. Where phi theta is the log normalizer. We call the triple mu Vt a realization of P. Some texts call this triple representation, but to avoid conflict with group representation, we call realization in this talk. Let's see a typical example, a family of normal distributions. This is an exponential family on R. In fact, we can take the realization mu Vt like this. This realization is not unique, but easiest one in the sense of the dimension of V. By definition, there are too many exponential families. However, only a small part of them are widely used, like this picture. Oops, sorry, it is too small to see. Let's enlarge here. Oh, good. There are good exponential families we often use. From this picture, we can expect there exist good exponential families. So we want a framework to understand good exponential families systematically. This is our motivation. The following observation gives us a hint to attain our purpose. Namely, useful exponential families have the same symmetry as the sample spaces. Mathematically, the sample space is a homogeneous space, G mod H, and the family of distribution is invariant under the induced G action. Here, G is a Lie group, and H is a closed subgroup of G. So our idea is to use representation theory, which is a theory of symmetry. Here, writing a space by the form G mod H is a description focusing on symmetry. For example, the real line can be described as a homogeneous space by taking affine transformation group here. which means real line has a symmetry of scaling and translation. Sphere is also a homogeneous space, which has a symmetry of rotation group, SO3. Upper half plane is also a homogeneous space, which has a symmetry of linear fractional transformation of SL to R. We proposed a method to construct exponential families by using representation theory. In this talk, we call it G-mod-H method. G-mod-H method has good properties. Namely, the method generates many well-known families, and moreover, families obtained by the method can be classified. So we can expect that new families obtained by this method are good. Now we will explain G-mod-H method. First, let us see a method roughly. Later, we will explain the method step by step. G-mod-H method is a method to construct a family of probability measures on G-mod-H from the following two inputs. One is a finite dimensional real representation rho from G to GLV, and the other one is a non-zero H fixed vector V0 with regard to this representation. Here GLV is a group consisting of all linear isomorphisms of real vector space V. We will see the details of G-mod-H method step by step later, but roughly speaking, we take the following 5 steps. In first step, step 1, we take Lie groups G and H. Here H is a closed subgroup of G, and X, which is a G-mod-H, and we consider X as a sample space here. In step 2, we take two inputs, finite dimensional real representation rho V and an H fixed vector V0. In step 3, we consider the set omega GH of all non-zero relatively G-invariant measures on X, which is compatible with group action. In step 4, we make measures parameterized by direct product of the dual of V and omega GH on X. In the final step 5, we normalize them. Before moving to each step, let us see examples obtained by G-mod-H method. Our method generates useful exponential families systematically, like this. In fact, by choosing these input GH, V0, we obtain these families. Here, choosing inputs GH, V0 is to give an interpretation of symmetry of the family of distributions. We mark that these are not all of examples obtained by our method. To explain each step of G-mod-H method, we would like to apply G-mod-H method to construct normal distributions in the top of this table. Now we enter the details of G-mod-H method. in the left side, we explain each step in representation theory. And in the right side, we demonstrate how the family of normal distributions is generated by G-mod-H method. In step 1, we prepare sample space with symmetry. We prepare sample space with symmetry in the representation side. We take a Lie group G and which describes the symmetry of the sample space, and the closed subgroup H of G, and the homogeneous space G mod H, denoted by X here. In the normal distribution side, R, the real line R has symmetry of scaling and translation. So we take the corresponding affine transformation group G and its closed subgroup H like this. Here the first component of affine transformation represent scaling, and the second component represent translation. Then we can identify G mod H with real line via this map. We will construct a family of normal distributions on real line with a well-known form. In step 2, in the representation theory side, we give input to generate distributions. We take a finite dimensional real vector space V and representation of G and non-zero H-fixed vector V0. Here G0, GLV denotes a set of all linear isomorphism of V. In the normal distribution side, we take the three in-depths like this, respectively. Here, Sim2R is the vector space of all symmetric matrices of size 2. We can easily check that V0 is H-fixed by considering the case X is equal to 0. In step 3, we consider measures compatible with symmetry. In the normal distribution size, a measure compatible with scaling and translation is essentially the Lebesgue measure on the real line. Mathematically, measures compatible with symmetry means relatively G-invariant measure on X. The definition of relatively G-invariant measure is given in definition 2.3. So we consider the set of all non-zero relatively G-invariant measures on X up to positive scalar. We denote it by omega GH. This depends only on pair G and H. We regard an element of omega GH as a parameter later. In step 4, we construct a measure on X with symmetry. More precisely, in the representation theory side, we define measures parameterized by the direct product of the dual of the vector space V and omega GH as follows. Here, rho X V0 is well defined because V0 is H-fixed. In the normal distribution size, by taking normal natural inner product on the space of symmetric matrices, we obtain measures parameterized by real numbers theta 1, theta 3, and theta 3, theta 2, and theta 3. In the final step 5, we normalize the measures above. We denote by large theta the set of parameters such that the measure is integrable on the whole space X. We call it parameter space in this talk. Then by normalizing the measures, we obtain the set of probability measures P theta parameterized by parameter space. In the normal distribution side, we can compute the parameter space like this and the normal log normalizer like this. And as a result, we obtain the probability measure like this. Namely, we obtain family of distributions on the real line as shown. Moreover, by changing variables here, we obtain the well-known form of normal distributions. Now, we see the properties of G mod H method. The family obtained in this way has good properties. Namely, the family obtained by our method is a G-invariant exponential family on G mod H. For example, in the normal distribution case, G action means scaling and translation. So this proposition corresponds to the fact that the distribution transformed by scaling or translation from normal distribution is also a normal distribution. Then the following question 2.5 naturally arises. Namely, are any G-invariant exponential families on G mod H obtained by our method? The answer is yes, under a mild assumption. So we accept the answer, roughly speaking, there is a correspondence between the set of G-invariant exponential family on G mod H and the set of families on G mod H obtained by G mod H method. For details, please see our paper if you are interested in. Now let's see related work in the field of machine learning. Cohen and Waring submitted a paper to ICML, which is a conference of machine learning. Their paper suggests harmonic exponential families on manifolds, on compact groups, or compact homogeneous spaces, such as circle or sphere. And use first Fourier transform on circle or sphere to perform gradient-based optimization of low likelihood for MLE. And apply them to the problem of modeling the spatial distribution of significant earthquake on the surface of the Earth by regarding the Earth as sphere. Let us see the relation, the method by Cohen and Waring and G mod H method. The paper by Cohen and Waring gives a method to construct exponential families on G mod H by using unitary representation of compact Lie groups G and G invariant measure on G mod H. Please remark that the method by Cohen and Waring can be regarded as a case where G is compact of G mod H method. In fact, in the case where G is compact, then relatively G invariant measure is automatically G invariant. So as a result, in the case of where G is compact, the method by Cohen and Reagan can be regarded as a special case of G mod H method. We leave take-home messages here. If you want a good family of distributions on some spaces, please tell us the spaces. We will try to propose good families of distribution on them. Thank you very much for your listening. These are references.
Okay, thank you very much. Any questions? So let me ask a question. So
okay.
I want to somehow draw some practical implication from your results. So can you go back to the final slide and
final slide.
Yeah, so this this new family. So from a machine learning viewpoint, how can we utilize this in like improving a method or generalizing a method?
You mean you want to know the application of these distributions?
Yeah, you could call it application.
For example, we want. I think the family of distributions on upper half plane or more general space, such as hyperbolic space, is not so many. So by suggesting family of distributions on that spaces, then we can perform the MLE on hyperbolic space or upper half plane. So
in a sense, we can run a machine learning algorithm in a natural way in upper half plane, for example.
Yeah. For example, we can use these family of distributions, for example, meta learning in the Bayesian setting, because if we consider the family of normal distributions, then we need to fix a prior mean and variance. Then by taking the x-axis as a mean and taking a y-axis as a variance, then we can use these family of distributions for meta learning.
Have you ever tried any experiments?
But I didn't run experiments. In fact,
yeah, that would be an important future work for you because this is one step further towards machine learning.
Yeah, so I want to we want collaborator, and if we have a problem on the machine learning on upper plane or hyperbolic spaces, then we want to collaborate.
Okay, thank you very much.